Hi, I'm Greg Elbing.
And I'm Matt Evanson.
We're talking about DNA cryptography. So mathematically, we've been talking about trapdoor functions. Those are things that it's really easy to go one way, but not the other way. With DNA cryptography, we're using a bunch of biological trapdoor functions, which you'll hear about later. DNA, of course, is the four chemicals you're all familiar with, and a DNA chip or a microarray has some variable number scores up to thousands of different dots. Each dot is an experiment with some kind of probe which things will bind to. Usually DNA, sometimes also other things that, proteins and whatnot.
So, first we have the asymmetric encryption and signature method with DNA technology. This paper suggests using DNA PKC, which stands for public key cryptology, in asymmetric encryption. In asymmetric encryption, the DNA PKC uses two pairs of keys. Using a public key encryption, anyone can send a message to a specific user. Only the specific user has the decryption key needed to decrypt the ciphertext. In the general method, keys are in the form of digital information, and in DNA PKC, keys take the form of biological molecules. So in the encryption process, you choose candidate probes, which would be DNA, protein, PNA. You keep experimenting to get good results. You want a good reaction or high reactivity to be your ones and a really low reactivity to be your zeros. The private and public keys are a mixture of like 32 DNA probes, so you do have, it's not just one strand of DNA, it's a many to many relationship, so you can get false positives. And you use this to fabricate your DNA chip, which is your cipher or your plain text or your ciphertext, and you convert your ASCII to binary, which are your ones and zeros, and you put that on the chip, and you make 6 copies on one chip, so you can make sure you get a good reaction, because a part of this is you can only try this a few times before you wash away all the DNA, which is part of the security. And then after you do that, you transmit the chip to the person you want it to receive it. So, to decrypt it, you hybridize with the sender's decryption key. So if you're the receiver, you get the decryption key from the sender, and you pour that over the chip, and it'll react. You scan that with the DNA chip reader, and it'll glow because it'll be highly reactive, and that'll be your ones. And then if it doesn't glow, those will be your zeros, and that's how you read your message. And this is an example of these chips. On the left is what a chip would look like if it was properly decrypted using the decryption solution. The light spots represent your ones, and the dark spots represent your zeros. And as you can see, the message does repeat 6 times. And on the right shows the result of the attempted attack on the chip, and you'll notice like the false positive and negative reactions due to the many-to-many property that DNA PKC does have.
So the second paper that we read was about dynamic broadcast encryption schemes using this method. So broadcast encryption is using the fact that DNA probes have this many-to-many relation that we've been talking about, such that we've got 32 different probes in one key, if you will, and so some of those might react to some things, some of those might react to other things. Some individual probes might react differently to different chemicals or to different other strands, and so you have to. This gives you this leeway basically to make different keys that will actually react to the same set, which can be really useful. This is actually how cable does its subscription broadcast encryption. So there's 7 properties that you have to have. 4 that I'm going to really focus on are: number 1 is that a user's decryption key cannot be used to determine other users' decryption keys. Number 3 is that if you hybridize a decryption key that is no longer in the set with the ciphertext, you'll get random results. It just won't work. Number 4 is that revoked users cannot decrypt future data, and that number 5, a new user cannot decrypt past data that's already been sent. So in an example, let's say that Alice has a private key PK1 which can be decrypted by Bob, Chuck, and Dan with K1, K2, and K3. Now later, let's say that Dan is maybe determined to be a spy, and so Alice changes her key to PK2, and now Bob and Chuck can read it, but Dan can't read it.
So the third paper is a little different than the first 2, where they send a physical copy. This one, the DNA is just used as kind of like a random number generator, and you use it to get 80 random bits of single-strand DNA as your key, and then you convert your plain text into binary, and then on the binary you perform the Feistel structure, where you cut it in half, XOR it, reconcatenate it. And so what you do to encrypt the message is you read from left to right from your message and right to left on the key, And when you run into a 1 in the message, you take 5 of those letters from the key and put that for the ciphertext. And if you run into a 0, you either leave a space or you put 5 random numbers or letters from the key. We weren't quite sure because this paper honestly wasn't that descriptive and great.
Along those lines, we actually found a lot that was wrong with this paper, and this is just the short list of it. First of all is that practically there's not enough DNA to even read, to even sequence this. Remember, this is a single strand of DNA that we're talking about here. Whereas, with the microdots, that's picomoles of DNA strands that you're dealing with in that level. This is also really susceptible to cryptanalysis if you are able to read it. Like they had kind of mentioned that this was, if it wasn't on single-strand DNA, then it was going to be, like you would just see the letters, and then that just becomes really obvious for cryptanalysis and very weak towards that. It's also really impractical to manufacture if you are doing this on single-strand DNA. Not like the 2 papers weren't impractical to manufacture, but this is also this is almost more impractical to manufacture than the other 2. Also, the Feisel structure does basically nothing, and if you realize that this is back a slide, that this is the structure that they're showing for the entire message, not per block, and so that's not great. Also, we found a problem in the decryption where if there are 16 zeros in a row, then it just doesn't work. You don't know if those were there or not, or if there's even more than 16. There's also currently no biological process or tools to be able to do this, so that doesn't help either. So the solution that we came up with for the first 2 papers, at least, is that we can use QR codes instead of, to represent the data instead of just straight up ASCII. One of the benefits is that you get data error correction in the QR format. Also, the speed of the machine reading can be increased, which cuts down on the time that you have to actually leave this thing in to read it in the first place. You can also choose your error correction level dynamically, so if you're fairly certain that this is going to be preserved well, you can choose a very low tolerance, or if you think that something might get smeared or hit or something, then you can have a really high error correction level. Now, QR version 40 is this big blob that you see on the right. It's 177 by 177 pixels, which gives you 31,000 different pixels. Now, that lets you have just over 4,000 alphanumeric characters in there. There's different levels of things that it can encode in QR, but alphanumeric, that gives you just over 4,000. Now, that's going to be just, if you do the math, that's about 7.6 pixels per character is what that ends up being. Or, yeah, so whereas on the left, since you're repeating this 6 times, that gives you 48 pixels per character. So that's actually quite a huge improvement in efficiency at this level. Are there any questions?